Hi everyone, thanks for joining me. First off, I just want to thank my co-authors on this study, Wilhelmina, Oscar, Walter and Loic, as well as the British Ecological Society Macroecology Group for putting on the conference and giving me the opportunity to talk to you all today. So to kick off, environmental energy is a really good predictor of biodiversity, but we still don't really know why. So one explanation for this relationship was put forward by Klaus Rode under the energy and evolutionary rates hypothesis. This hypothesis argued that high environmental energy or temperature drives faster rates of mutation and/or faster life histories. These factors contribute to faster rates of molecular evolution, which might lead to faster rates of speciation. This hypothesis is compelling because it links micro-scale processes to macro-scale patterns. However, it's been elusive to test so far due to its complexity. In this study, we wanted to test for a signature of the evolutionary rates hypothesis in terrestrial vertebrates using simulation models that explicitly incorporate ecological and evolutionary processes. To do this, we used a spatially explicit simulation engine, Genesis, which is basically a tool to construct forward-in-time simulation models on gridded landscapes. This allows us to incorporate real paleotemperature and aridity reconstructions into the model to assess how diversification dynamics have played out in conjunction with environmental and plate tectonic changes. So simulations allow us to imagine alternate versions of the evolution of life on Earth to understand how real biodiversity patterns, such as species richness, which you can see on the bottom, and how they might emerge. So we model in Genesis 4 core processes, including dispersal, trait evolution, ecological interactions, and speciation, which I'm going to touch on in a bit more detail. So in Genesis, speciation occurs between allopatric populations. These populations diverge genetically from one another at rate lambda and become new species when they cross a threshold S. So for this study, we modeled 4 different submodels of population divergence. One where lambda is a function of temperature that the populations are exposed to, alternatively body size as a proxy for life history, or temperature and body size. And finally, we compare this to a null model in which lambda is independent of temperature and body size. So the specific aims and questions that we wanted to answer were, do biodiversity patterns differ between these population divergence submodels? If so, which biodiversity patterns are diagnostic of these different submodels? And what is the relative support for each model based on empirical data? Okay, I'm going to skim through the methods, but I encourage questions later on. The simulation model gives us data that's directly comparable to real biodiversity data. This is species distributions, phylogenetic relationships, and traits. From this, we can summarize different patterns using metrics. For example, correlation coefficients between temperature and species richness, or indices of phylogenetic tree imbalance. We can estimate how much information content there is in the metrics using machine learning classification tools, and then attempt to predict the submodel of population divergence in empirical data by extracting the same summary metrics. So our first aim was to see whether biodiversity patterns differ between these submodels of population divergence. And the short answer is yes. The panel on the right shows the distribution or the mean values of different summary metrics, and we can see that many of these show distinctly different means. And this allowed machine learning algorithms to accurately predict the correct model of population divergence in more than 70% of simulations. However, different metrics contributed differently to this discrimination ability. For example, there were really informative metrics such as tip rate correlations, so diversification rate and body size correlations. And there were some really uninformative summary statistics, for example, spatial diversity patterns, including correlations between species richness and temperature. This brings me to the final aim, which was to test the relative support for the evolutionary rates hypothesis in terrestrial vertebrates. So on the right, you can see the phylogenetic relatedness of 46 different terrestrial vertebrate clades and the relative support of each population divergence submodel from the machine learning classification tools. What we found was that 30 of these 46 clades showed support for a temperature-dependent model, that's M1, and a further 8 showed most support for a temperature and body size dependent model, M3. Now what you can see is that from eyeballing this, there's no obvious taxonomic pattern. It seems to be widespread throughout the tree. So our main conclusions from these results are that temperature dependency of speciation rates seems to be a widespread phenomena in terrestrial vertebrates. And this is what we're considering partial support for the evolutionary rates hypothesis. It also leads me to point out that simulation-based inference methods offer a cool new frontier in macroecology and macroevolution. So if anyone is interested in these methods, but they don't know where to start, please feel free to drop me a line. And yeah, thank you all for your attention and enjoy the conference.